Okay, so let's suppose that our particle, so suppose the particle has mass m, right, and that it's moving under the influence of some acceleration, or moving with acceleration a of t. Okay, then using Newton's second law, well, we can talk about what the force that our particle experiences is. Well, you guys might remember, this is the famous F of t. Well, F equals ma. Okay? So, once again, just to reiterate, if we have a particle with mass m moving around with acceleration a of t, then the force it experiences is given by F equals ma. And, of course, the force is a vector quantity, since the acceleration is also a vector quantity. So now let's do an example using Newton's second law here. Right? So our situation here is we're firing a projectile, and since it's from a cannon, let's say we're firing a cannonball from a cannon, and it has a muzzle speed of 200 meters per second, and the angle of elevation of the cannon is 60. Right? And this cannon also happens to be raised 10 meters above the ground. Right? We want to find out how far from its starting place, sort of horizontally, has this cannonball traveled. All right, so let's draw a picture of the situation. That should, always help figure out what's going on. Okay, so let's say down here we have our grass. Actually, let's make this a bit longer too. Right? Okay. Over here, we have a stand, right? And on top of this, we have a cannon, right? So what are each of these numbers meaning? Well, to start with, so since the muzzle of the cannon is here, that means this distance is 10 meters. Right? So that's how high off the ground the cannonball is leaving the cannon. Right? This angle of elevation of 60 degrees, well, I don't think I drew this cannon quite at 60 degrees, but what that means is that this angle here is 60 degrees. So this picture isn't quite to scale, but it gets the idea across. Right, and then what's going to happen in this scenario? Well, the cannonball's going to fly out, and then it's going to land somewhere. Let's make our grass here a little longer. Right. It's going to land somewhere out there after traveling in a parabolic shape. And what we're looking for is this distance here. This is the distance we want to look for, right? This will be the distance covered by the projectile, or in this case, the cannonball. Okay? So let's look at the setup going into this. Well, this cannonball is fired. And what are the only forces acting on this? Well, being good mathematicians here, we've assumed that all forces except gravity are negligible. All right? And I think in like the very basic physics courses, you'll probably do this too. But later on, you'll want to include things like drag. But for now, the only thing acting on this projectile is gravity. That's the only force it experiences. So the force, well, what is force? It's mass times acceleration. Right? And in this case, mass is, well, mass is just the mass of the projectile. We'll call that m still. And what's the acceleration due to gravity? Well, gravity doesn't push you left or right or forward or backwards. All it's doing is just pulling you directly down to the surface. So in this 2D picture, what gravity looks like is negative g in the j direction. Right? So that's telling you, let's say if our cannonball, when it's up here, the force it's experiencing, F at this time, is going to be minus gmj. Or maybe I should say mgj. Right? So the only force it's ever experiencing is going directly down. All right. Well, what we really need to get at here is the position function. Okay? So, well, we have this force here. We can use this to find the acceleration, right? Using this piece of the equation here, this will tell us that the acceleration is just the acceleration due to gravity. So minus g times j. Okay? So now we have to, integrate this, get the velocity function, and then we integrate it again and get position function, right? Just like in the previous example. Except now here, where is our initial velocity? Well, it's actually encoded in two pieces of information. Up here in the muzzle speed, and here in the angle of elevation. That'll be the initial velocity. Right? So the initial velocity is starting here at this point, and the magnitude of the velocity is 200, and the angle of it is 60. So what does that tell us? This tells us that, let's use a v sub naught, or, well, we could do that. Let's do this, v of 0. This is going to be the initial velocity, right? And if you remember from our earlier section, if we know the magnitude and the angle of a vector, or the direction, we can find the vector. So in this case, we're going to have 200 cosine 60 degrees in the I direction, okay, plus 200 sine of 60 degrees in the j direction. Right? This is just using what we know about creating the component form of a vector from its magnitude and direction. Okay. So let's write this out here. Cosine of 60 degrees is 1/2. So this is 100 I plus, and we're actually going to have 100 square root 3 j. Okay? So that's going to be our initial velocity. And now we're going to do what we did before in the last example. We're going to integrate the acceleration and then compare that to our initial velocity here to get the actual velocity function. So let's go ahead and do that. And let's change colors to do it. Right? So down here, the velocity at time t, which is the integration of acceleration, okay? Well, if we integrate this, all we get is c1i plus minus gt plus c2j. Okay? All right. So now we plug in 0. So v of 0. Plug it in here. We have c1i plus, well, just c2j. Right? And this has to equal 100i plus 100 square root 3j. All right, and this will tell us immediately what C1 and C2 are. It's pretty easy here. So, wait, let's write that here. C1 is 100. C2 is 100 square root 3. And let's take these two and plug it in up here. Right? So that and let's use a different color here as well. Okay. So that tells us our velocity function is 100 I plus 100 square root 3 minus gt j. Okay? So that gives us our velocity function. And now we'll need to start this over and do the position. Okay? So now we have to integrate the velocity function to get the position function. But when we do that, just like in the last example, we need an initial position to work with as well. Well, it's not explicitly given here in the example this time. That means it's hidden somewhere in here in this information, just like the initial velocity was. Right? And this one is maybe a little less tricky than the initial velocity in that it's right here. Right? It's just the initial position, right? Which we can assume that the initial x position is 0 since we're wanting to calculate distance from here. But since this is ground level, we want to assume then that the initial position, the initial y position, or j position, is 10 meters in the air. So what that means is we're going to assume that r of 0 is 10j. Right? That corresponds to this here. All right, so now let's go ahead and integrate v of t and get the initial position. So we integrate r of t, integral of v of t, right? And that's going to be 100 t plus c1i plus 100 square root 3t minus 1 half gt squared plus c2j. Right? So you might start recognizing this kind of stuff from if you studied the kinematic equations in a basic physics class. Okay, so now we're going to use our initial position, plug it in here to get rid of c1 and c2. Okay, so let's start by plugging in 0. R of 0 will be c1i plus, well, this thing's going to be 0 and this thing's going to be 0, so we just get c2j. Right, and that has to be 10j. So that implies c1 is 0, c2 is 10. Right? So from that, we get the actual position. R of t, this is going to equal 100. Actually, we don't need this parenthesis here. So 100 t 100 ti plus 100 square root 3t minus 1 half gt squared plus 10j. Okay? All right, so that's the that's the actual position function for any time t. At least we're assuming t equals 0 is the instant it's fired from the cannon. So this is really just valid for t greater than or equal to 0. Okay? All right. So what do we need to do now? Well, remember, what are we looking for? We're looking for this distance here. Okay? Well, how do we find that distance? Well, what happens here is we need to figure out what time it hits the ground, right? Because the time it hits the ground here, if we plug that into the x component, or the I component of our position function, that'll tell us how far it's moved. Okay? So what does that mean? Well, that means we just take the j component, which takes care of the altitude, if you like, or the height, and we want to figure out when it has height 0. That's not too bad. So let's go ahead and do that. And so I'm going to kneel down here, and we'll do this. Okay, so let's write this in the form of a usual quadratic equation. We have 1/2 gt squared, okay, plus 100 root 3 t plus 10. And we're trying to solve when this is equal to 0. All right, so you remember how to solve that? Not too bad, just the quadratic formula. So t is negative b, so negative 100 square root 3, okay, plus or minus the square root of, what is it, b squared. So we have a quite large thing here. So this will be 10,000 times 3, so 30,000, all right, minus 4ac, so minus 4ac, so plus 20g, okay? And all of this is over 2a, so all of this is divided by minus g. All right, well, we have two possible solutions in here. Which one do we want? Well, think about it. One of these is a negative t value. The other one's positive. Okay? So t equals 0 is here, and positive time goes this way. Well, what that means is we want to take the positive t value. That corresponds to taking the minus here, because there's a negative g on the bottom. So if we take the minus square root, then we'll get a positive time t. Okay? So let's move over here and do that. So t, the time we want is minus 100 square root 3 minus square root 30,000 plus 20g. Well, actually, let's switch this up. The minus from here will get rid of the negative on the top. So now it actually looks like a positive number, right? And because it's nice to have actual numbers for things, this value of t, we're going to use, by the way, g is about 9.8. If you want units, of course, meters per second squared. Okay? So t here will be about 35.4 seconds. Okay? So that's how long it takes to get from the instant it's fired here all the way till it hits the ground over here. All right, well, that means all we have left to do then is plug that time into, where'd it go? Here, to see, well, what's the horizontal displacement after 35.4 seconds? All right, so this distance d here, this d, let's do it right here in front of me. I'll move over here. So d, this will be 100 times 35.4. Okay? Right, so we're just plugging it into the I component here, right? Because that'll tell us, again, the horizontal distance, right? So that's just 35.40, and this will be in meters. Right, so 3,540 meters. 3 kilometers. That's that's quite a strong cannon, right? I mean, firing at 200 meters per second, that's quite a lot. Okay, so this is a little bit unrealistic, but the concepts show through. Okay? So hopefully this all made sense.